So in this video, we're going to discuss Green's theorem to find outward flux of the vector field that is given to us right here, component-wise, across the curve C that is represented by this equation. All right, so first thing I'm going to do is state what is the outward flux version of Green's theorem. So that is going to be the following. So hopefully you have seen this. This is the line integral along the closed curve C of f, the field, dotted with the unit normal of the curve, ds. This can be written as the line integral along the closed curve C of, now if I were to label my components for the field as a following function, so let's call this function to be P, this function to be Q, then my Green's theorem version would be P dy minus Q dx. And this is equal to the double integral over the region that is enclosed by the curve C, let's call that region D, of the divergent of the field F dA. Now divergence, we're going to define it in the following way. So the divergent of this field, this is going to be the P sub x plus Q sub y. That is what the divergence of the field is. Okay, so that's what I'm going to show you how to calculate the outward flux of this vector field along this curve. So let's go ahead and draw the picture of our region and the curve C. So notice that this is a circle of radius 2. So we're going to draw a circle center at the origin of radius 2. Let's suppose that is the circle. So this is 2. That is our boundary of the curve C. And the region we're interested in is, of course, inside this circle. So this is our region D for the double integral. So because this is a circle, we're going to express region D in polar coordinates. So D is going to be expressed as a polar coordinate r comma theta, such that r is going to be from 0 to 2, and theta is going to go all the way around the circle. That's from 0 to 2 pi. So that's how we're going to describe this region D. Okay, so the next thing we're going to compute, so since we are using Green's theorem, we're going to set up the double integral rather than this, because that's what the line integral is equal to. So we need to define what is P sub x. So from the field, we're given the components x negative y squared. So as you see it in the earlier of the problem, we said this is our function P, this is our function Q. So we're going to compute the divergence of F. So we need to find P sub x, that's the partial of P respect to x. So if I take partial of P respect to x, I'm going to get 1, and then Q sub y. So we're going to compute the partial of Q respect to y. That is going to be negative 2y. All right, so that's what we're going to substitute into the integrand right here, and then we set up the double integral. So by Green's, we know the outward flux, it's the single integral, so we know it is a line integral of f dotted with the unit normal ds. This is equal to the double integral over this region D enclosed by the curve C of P sub x plus Q sub y dA. So we're setting up D as a polar coordinate. So this is going to be the integral from 0 to 2 pi. That's the bound on theta. Then we have the integral for 0 to 2. That's for r. Then P sub x, we know that's 1 plus Q sub y, that's negative 2y. And then we have r dr d theta. That is our expression for dA in polar coordinates. So note that dA in polar is r dr d theta. All right, so once you have all of that done, you're pretty much ready to integrate. But there's still one more thing left to change in the integrand is this, y. Well, we know y in polar coordinates is r sine theta. So I'm going to make that replacement, then we're ready to integrate. So our Green's theorem gives us the integral from 0 to 2 pi, and the integral from 0 to 2 of 1 minus 2r sine theta times r dr d theta. And then you can distribute this r out to each component inside. So this will simply give us, here you will have an r, then we have r squared, then sine theta, dr, d theta. And now we finish up the integration. So this is going to be the integral from 0 to 2 pi. So first we integrate each of these with respect to r. So that would give us r squared over 2 for the first term. For the second one, we have 2r cubed over 3 sine theta. And then we evaluate from 0 to 2 d theta. Now plug in for r, each r, you're going to plug in 2 and then 0 using the fundamental theorem of calculus. We evaluate. So we have the integral from 0 to 2 pi. So plug in 2, you have 4 over 2. That would be 2 minus 2 cubed. That's 8 times 2. That's 16 over 3 sine theta. And then when I plug in the lower limit 0 into each of these r values, I get 0. So we have to just write this. Okay, so next thing is to now finish up integrating respect to theta. So when I integrate to respect to theta, I have 2 theta. When I integrate negative 16 over 3 sine theta, that's going to give me positive 16 over 3 cosine theta, because the integral of sine is negative cosine. The negative canceled out. All right, so that is what we have. Now we evaluate from 0 to 2 pi. So plugging in 2 pi for each theta first. So you'll have 2 times 2 pi plus 16 over 3 times cosine of 2 pi. And then minus, when you plug in 0, for theta, you have 2 times 0, and then plus 16 over 3 times cosine of 0. All right, so that's finishing up the substitution. So we know this is 0. Cosine of 0, we know that's 1. And we know cosine of 2 pi, that's also 1. So this is 4 pi plus 16 over 3 minus 16 over 3. All right, so this will cancel out. So we have just 4 pi. All right, so that is our outward flux. All right, I hope this makes sense. See you next time.